Okay, I guess we're back. I don't, yeah, all of a sudden my computer was freaking out. Yeah, it's a PC, which as you know, stands for piece of crap. Um, it's more than a year old, which means it's ready for the junkyard. I just haven't gotten around to buying a new one yet, or which no, maybe I should just not buy a new one at all and just stick with the Mac. But unfortunately, I'm stuck with this thing for the time being, so we'll have to keep putting up with it. Let me just get everything open again. Yeah, that's what you get. You think you're saving money with the PC, you're not. All right, let me get everything open. And by the way, you might discover that the recordings, in a case like this, what might have happened, yeah, it's all gone. What could have happened, if you see there might end up being or at least two parts of the recording, it's possible that it got interrupted and it started a new one. So if you see two of them there, that would be the reason. I've had this happen to me before. The thing is, I would go into the Mac store, the Apple store tomorrow and get a new one, but it doesn't work that way anymore, apparently. You now have to go order it online, and then it could take now up to a month to get a new one. I have no idea why, but that's the way it goes these days. All right, let me get this going here. Oops. Uh, that would be chapter 3. Oh, no. Yeah, I can tell this is going to keep happening. All right, well, we got that one saved. So we'll have to start it all over again, unfortunately. I was about to give you a nice Excel lesson, and this is what happens. All right. We also, of course, need the slides. Let me get those again. All right. So we didn't really actually start this. Okay. All right. I think we're safe now. This is another reason why you have to save everything extremely frequently. All right, so let's get back to covariance. Yes, so all right, so at least we got through this part. So what I was about to do is go through and show you how to do this in Excel, and then how to understand what are the strengths and weaknesses of these measures and what can we do about it. All right, so let's do this one more time. See, the thing is I didn't have a chance to save it, and that's why, of course, it's all gone. You don't save stuff every at least 2 minutes or so. Just asking for trouble. All right, so let's try that again. Insert. All right, so we saw already that the graph shows us that the connection between the two variables is not particularly strong. It is negative, but it's hard to tell what that means without looking at this plot. All right, there we go. So once again, we do have a very almost flat. It is negatively sloped, but just barely. And that's what we're concerned about, because this is actually building up to one of the real weaknesses of the covariance measure. And that is that it's difficult to interpret this number. In other words, the covariance shows the direction of the relationship between X and Y. And when I say the word direction, I mean positive or negative. But it is difficult to interpret the strength of this relationship from the covariance measure. This is because the measure has no upper or lower limit. So in other words, it's hard to tell. I mean, -1, is that a strong or is it a weak relationship? It's very difficult to be sure. And so that's one of the real problems with the covariance measure. And in addition, there's one other problem we run into. In addition, the covariance measure is affected by the units of the data. Now, what do I mean by that? Let me show you an example of this. Suppose that these are, in fact, temperatures in Celsius. What I'm going to do is convert them into Fahrenheit, and I want you to see what happens. Let's just say so let's say, for example, here now, the reform, you might remember, you learned this somewhere along the way, it's 32 plus 9/5 times the Celsius temperature. Okay, so this is the equivalent value in Fahrenheit. Now, I'm going to recalculate the covariance. Now, I want you to see what happens here. You might think, well, what's the difference? It's just a unit, right? Oh, hold on a second. I've done it wrong. Sorry, it's I3 through I7, comma, J3 through J7. Okay, now look what happened. It's different, isn't it? And so you can see that the covariance itself, the value of the covariance is affected by the units. And that is a very awkward thing, because now when you look at this number, you have to ask yourself, well, what does that mean? Does that degrees? Is it Celsius? Is it Fahrenheit? Not only that, but if we scatter plot this, let's see if it makes a difference in the way it looks. Let's see. Yeah, now look at that. That's a kind of a strange result there. Now, part of the reason for that is because the numbers are larger. There's a way we can get around this. Watch what I'm going to do. I'm going to ask it not to show any numbers on the horizontal axis smaller than 20 or smaller than 30 on this axis. So yeah, it's starting to look a lot more like the other one, but you can see the magnitudes are different. And so it's actually, let me change this one to 25. Yeah, it's just, it's hard to be sure. They're similar. They're not identical. Let me just change these titles. Anyway, so what this means then is that the covariance, not only is it hard to interpret the number, but the units affect the result that we get. So these are very awkward problems. So what do we do about it? Well, guess what? We have another measure of association which gets around both of these problems. Okay, and what is this amazing measure? It is called correlation. Now, before, oh, by the way, I almost forgot. With the sample covariance formula, there's a corresponding version for populations, which I'd like you to see before we start talking about correlation. So what I'm going to do is have these side by side, and you can see that just like with the variance, there's a difference in the notation between the sample and population versions, but just like with the variance, there's one key difference numerically, and that is that we're divided by n instead of n minus 1. All right, so first I have to quickly plug in my tablet here so you can see what I'm doing. It's being stubborn with me, of course. Hold on one second. I just want to make sure I've saved these where I thought I did. Oh my God. Yeah, they're on there. Let me just do one thing here. All right. Oh, it actually allowed me to eject my flash drive. How about that? All right, now I have to go get those things back. Hold on. Wait a minute. boy, this is the day, I'm telling you. All right, it's actually letting me look at my files. All right, here we go. Let me get these back open again. So I wanted you to see the differences between the sample and the population covariance. And like we said before, just like with the variance, the differences come down to two things. Number one, the notation. And you'll see that we have replaced SXY with sigma XY. So you might remember these were earlier used for the sample standard deviation. And this is the population standard deviation. So here, and by the way, the sigma is the Greek version of S anyway. So that's why we see these two always associated with each other. And the subscripts are there to remind us this is not the standard deviation any longer. This is the population covariance. Now, if you notice, we've replaced X bar. Now here, if you see for the first time, this mu has a subscript. That's because we have two different populations and we have to know which is which. So this is the mean of population X. In the past, we did not have a subscript because we only had the one population. Now we have to make sure we know which is which. And then, of course, that means that this is the mean of population Y. And of course, and also don't forget, capital N is the population size. But this is also the distinction we saw with the variance measure. With the sample case, we divide by n minus 1, and with the population case, we divide by n. But otherwise, it's the same thing. All right, so now that we've seen that, we can go on and take a look at this other measure of association called correlation. Now, correlation, as it turns out, will prove to be the more useful of the two measures. Why is that? Well, two things. It offsets the problems that we ran into with the covariance. I'll just note these here. The correlation, number one, because of the way it's defined, the range of possible values is restricted to -1 to +1, which makes it much easier to interpret than the covariance. All right, we'll see that why that is true in a minute, but correlation measure, or sometimes it's called the correlation coefficient, has a range of values from -1 to +1, making it much easier to interpret. Okay. Now, oh, wait a minute. I just confused it. That negative, oops. It doesn't like a negative at the front of the line. There's a way you get around that, though, by putting an apostrophe there. Okay, so that's a huge deal. Not only that, as if that weren't enough, it also has the benefit that the correlation measure or coefficient has no units. Okay, there aren't any. So it doesn't matter what data we're using, the correlation will be the same whether it's Celsius or Fahrenheit. We'll prove that in a second, by the way. So here's what I'm going to do. Let me actually calculate that here in Excel before I show you the formula. And you'll see what I mean. So it's called correlation, or in Excel, it's Correl. And we apply it to here. And it's -0.2. If I come over here with that same formula, it's still -0.21. You see how nice that is? Because it's not affected by the units. And on top of that, we know that this number is not that large compared to the maximum value of -1. So what I'm going to do is show you quickly what these numbers are actually telling us with some scatter plots. Okay, now if we had two variables whose correlation is +1, it would mean that all the points are exactly on the trend line, no exceptions. Okay, but at the other extreme, you would have a correlation of -1 means the opposite. Well, I mean, not exactly the opposite, but it means that the negatively sloped line, all the points are exactly on it. So this represents the two extreme outcomes. Here, the variables are said to be perfectly, positively correlated. Over here, we would say that X and Y are perfectly negatively correlated. So those are the two extreme outcomes that we can find. So let's look at some other cases besides these extreme possibilities. Okay, so just remember, +1 means they're all on a positively sloped trend line, and negative, perfectly negative means the opposite. Okay. Oh, rounding. I would say anywhere from 2 to 4 is probably good enough. Because we don't need to be that precise. I tend to use 4, but 2 is probably good enough for a case like this. So it's not something you need to worry about too much. But just me personally, I like 4, but you can use 2 if you want to. You know, it's not like certain cases, it's obvious, like with dollars and cents. Well, obviously, we know you're using 2 decimals. But here, you know, anything from 2 to 4 is fine. All right, let's look at some other cases. So how about this one? Suppose that the points are close to the line, but they're not all quite on there. They're really close though. Well, then you might, and I'm just making this up, but let's say in this case, the correlation is 0.9. It's a very strong, not perfect, positive relationship. We can say there that X and Y are strongly, not perfectly, but strongly, positively correlated. But then what about this case? How about if the points are not terribly close to the line at all? I mean, sure, they're moving in a positive direction, but man, there's a lot of gaps between those points in the line. That suggests that while there's a positive relationship here, it's not that strong. So let's say that here we have a case where the correlation is 0.2. Then we would say that X and Y are weakly, positively correlated. And then you can have a lot of, I mean, you know, and you get to intermediate cases where, you know, like 0.5, for example, they're somewhat strongly positive correlated. But I just wanted you to see that two positively correlated cases can be very different from each other. In the first case, X and Y are very closely related. In the second case, they're only weakly, but still positively related. All right. Now let's look at the negative cases. You could probably guess what's coming. Let's say we have a very strong, but not necessarily perfectly negative relationship here. We would say that X and Y are strongly but negatively correlated. And let's just say this time the correlation is negative 0.8, let's say. Still, it's awfully close to -1, but it's not quite there. And then you know what's coming next. Oops. Let me just quickly save this because you don't know what might happen with this thing. All right, let me try that again. And then let's say here's the trend line and the points are sort of negatively correlated, not a very strong relationship at all, but they are negative. Let's say it's negative 0.1. Boy, that's pretty weak. So X and Y are weakly, but still negatively correlated. But you can tell just by looking at that number, it's negative, which is obvious, but it's a small negative number, which means you really don't even need this graph to realize that this is a very weak negative relationship. With the covariance, what if the number was -5? Well, it's impossible to know if that's strong or weak without seeing the graph. But here, the number itself is telling us how strong that relationship is. So this is a huge advantage over the covariance. All right, now, let me show you one final case. What if the points are just all over the place? There's no pattern to them at all. It's like you open up a bottle of Perrier and you look at the bubbles bouncing off the surface of the water. That's what it makes me think of, Perrier. The trend line is flat. The correlation in this case is 0. So you could say that X and Y are uncorrelated. Or independent. Now, by the way, this works for covariance too. 0 means independent for both covariance and correlation. So this means two variables that are absurdly unrelated. Like, what if the variables were GPA and shoe size? Obviously, there's no connection there. So if you plotted something like this, you'd get a bunch of random points because you're going to get people with high GPAs and big feet and people with low GPAs and small feet. And you're going to get people with low GPAs and big feet. And, you know, every combination is possible. Okay, so you can see now that the correlation is easy to interpret. And so now we can go back to our last example and we'll see that, wait a minute, that makes sense. This is not a very strong relationship. It is a weak negative relationship. And you can tell now just by looking at this correlation, negative 0.21, that's a weak negative relationship. And so we should not be surprised. So the -1, who knows what that means? But this is very meaningful to us. We can tell right away that this is a very weak negative relationship. And this is why the correlation is usually the preferred choice of measures of association. So, well then, why do we even bother with the covariance? Well, here's why. Let's take a look at how the correlation is actually calculated. We'll start with the sample case, and guess what? It starts with the sample covariance, rather. How do you know? Because of those two subscripts. Now, here's something a little new. Remember, we've been using S to represent the sample standard deviation. When I add a subscript to that, that is simply to tell me which sample I'm referring to. This is the standard deviation of sample S. And this is the standard deviation of sample Y. Oh, what did I do? I wrote sample S, sorry. I meant X. No, X, God. All right, much better. And over here we have the standard deviation of sample Y. And now R with the two subscripts means sample correlation coefficient, which, as we know already, is bounded between negative and positive 1. It cannot fall outside that range because of the way it's defined. Now, that's done on purpose, by the way, to make sure that the value is always between negative and positive 1. So this correlation measure is the preferred of the two, but we still have to calculate the covariance first in order to come up with our correlations. We can't just completely ignore the covariance, but most of the time we'll use the correlation instead. Now, of course, if you're using Excel, you don't have to bother with the covariance because it has its own formula for the correlation. But of course, even Excel is using the covariance to come up with this correlation. All right. So in the slides, I'm showing you the details that you would need to come up with this correlation that I found in Excel. How was that determined? Well, we take the starting point as our sample covariance of -1, and then, now this is the only unfortunate thing, there's a lot of extra work here because you have to now calculate two different standard deviations, one for each of the two samples. Okay, so I get it. I guess this is good practice, but it's still a lot of extra work. So this is one of the only, I guess, negative things about correlation is that it has these extra steps. So here you can see that I've calculated the sample standard deviation for X. And you can see it's the formula we had earlier. And then the corresponding value for Y, you'll see in a minute, is this. You're just replacing the X's with Y's, that's all. And I've done that on the next slide. Okay. All right, so here we go. And you can see it's approximately 2.2361. And then on the next slide, I'm going to bring them together. So I'll give you a minute to catch up. And when I bring them together, there we go. There's your negative 0.2108. And now we know everything we need to know about the relationship between X and Y. It's a weak, negatively correlated relationship. All right. Now, of course, there's also a population version of this formula. Well, luckily this time it's exactly the same as the sample version, except for the notation. In fact, why don't I copy them so you can see them together side by side. And you see there's only one new thing here. These are the population standard deviations on top of the population covariance. And then these are the population, I'll just note that these are the population standard deviations. Here's something new. This is a new Greek letter for us. This is the Greek letter rho. Whenever you see rho, that means you're talking about correlation. You almost never see this letter used for any other purpose. So the two subscripts, by the way, because if rho is understood to represent correlation, then in principle, these subscripts are not really necessary because we're not using that letter for any other reason. So in a lot of books, you'll see rho written without the subscripts. It's understood that this means correlation. These are different because they're used for multiple purposes. You have to make sure you know which is which. They need subscripts. This one doesn't. So sometimes we'll use it, sometimes we won't. But just remember, this is always going to be the population correlation coefficient. Oops. All right. Well, you know what? This chapter is done. That means we can dive into chapter 5. Oh, by the way, don't forget, we've decided that because this is Christmas week coming up, or Christmas is coming up, you can have until Tuesday to do the chapter 3 problem set, which you now know how to do from start to finish. And we'll figure out 5 later on. But in the meantime, you're going to open up chapter 5 and see what that's all about. Also, this is an updated version of this spreadsheet. I'm going to post this on Moodle so you can look at them both. And in fact, if you want, you can use this as a template and make up your own graphs or fool around with these graphs just to get your hands on Excel, because like I said, Excel is such a powerful tool that if you're majoring in anything even related to business, you'll get an awful lot of use out of it. So that's a hint. Learn Excel. It can only help. You know, it's just one of those things where, it's like driving. I don't know if you have driver's licenses or not, but it's one of those things where even if you live in Manhattan, you really should have a driver's license because you never know when it will come in handy. And the same thing is here. You never know when you might need Excel. I thought that was a good analogy. I just dreamed that up on the spot. Okay, so those are updated. So now we're going to look at 5. And 5, I mentioned yesterday, I guess, that 5 is very, very different than 3. The focus is more on conceptual concepts rather than grinding out a bunch of numbers. Okay, so let me just save this real fast. 22nd. All right, we're ready. So now it turns out that probability theory is heavily based on a branch of mathematics. I'm sorry, statistics is heavily based on a branch of mathematics called probability theory. So we often, at some point early on in the course, take a little bit of a detour into this area of probability theory because everything that follows really ultimately comes down to what we're seeing in this chapter. The first part that we were discussing, the measures of central tendency and all that, that's an important introduction to the topic. But before we get too deeply involved in statistics, it's important to have some basic understanding of probability theory and what it's all about. Because ultimately, remember, statistics is really designed to be a very useful discipline. The idea is that it's helping us understand what's happening in the real world. And probability theory, to a certain degree, is the same. The idea here is that we're trying to come up with a framework for measuring uncertainty. And so that's really what this is all about. Now, some people will find this more interesting than chapter 3 and some will not, but here the focus is on the concepts rather than grinding out a bunch of numbers. So we start out by imagining that some type of a process is taking place, which we're going to call a random experiment. Now, that could take a lot of forms. There's a lot of types of random experiments that could be performed. And some of them are structured so that we know before we even start what types of outcomes might take place. And on top of that, in many cases, we also know the probabilities of those outcomes taking place, but not necessarily. The key here is that with a random experiment, it's important that we know upfront what might happen. But of course, we don't know what will happen until this process actually starts. So what kinds of things qualify as a random experiment? Well, there's a very wide range of possibilities here. Now, it's easy, by the way, to make up examples with games of chance because the rules are very well understood. For example, if you've ever seen a roulette wheel, in fact, where you haven't, we can go look at a picture of one. This is a game which you often find in casinos, but you can play this at home too if you have a roulette wheel. And essentially what's happening is that you just got this big wheel with numbers. Here we go. And so you throw a little ball in there and spin the wheel, and eventually the ball lands in one of these slots in front of the numbers. And that's how we decide who wins and who loses. Now, the key detail here is that if you notice, there's numbers ranging from 1 to 36, of which half are red and half are black. We also have these two extra numbers, 0 and 00, which are green. And so when you play this game, you can bet on anything you can imagine. You can bet on each individual number. You can bet on evens. You can bet on odds. You can bet on reds. You can bet on based on black. You can bet on ranges of numbers like 1 to 10, things like that. You can bet on anything. And the payoffs depend on the odds of that actually happening. But from our perspective right now, the key detail here is that each of these numbers is equally likely to come up. So let's say, for example, the probability of getting 00 is 1 out of 38 because there's altogether 38 numbers on this wheel, of which each is equally likely to occur. So if I spin this wheel, I'm performing a random experiment. Now, we may want to sit down and figure out, based on this information, the probability of getting, for example, an even number or a red or a black. We can do that with our probability theory framework. And so it's not difficult because in here, like I said, each number is equally likely to turn up. So for example, getting a 00 has a probability of 1 out of 38. Or choosing a deck a card from a deck. We're all familiar with the deck of cards. There's 52 cards. Each card is equally likely to be chosen. So I could ask myself, for example, what's the probability of picking a king or the 8 of hearts? It's easy to figure out because I understand how the deck is structured. And also, I know that each card is equally likely to be chosen. Also, I'm sure every one of us has in our lifetimes played games that involve dice, all right? And usually you roll a pair of dice. And because you're usually adding them up, the range of possibilities is from 2 to 12. Because each die contains the numbers 1 through 6. Now, here though, unlike the first two examples, the chances of getting any of these numbers is not the same. You probably know that, for example, the most likely outcome is 7, and 2 and 12 are the least likely outcomes. So it's a very different situation than the first two we have here, because the numbers 2 through 12 are definitely not equally likely to occur. But we can sit down and figure out what each probability is. So all of these could constitute random experiments, but it's a more general idea than just that. You could, as a random experiment, for example, survey people about whether or not they like a new product. Everybody's either going to say yes or no. And so we may want to understand what's likely to happen when we ask people about a brand new product that we produced recently. Or there's all kinds of possibilities that could qualify as a random experiment. So in this chapter, we'll be assuming that a random experiment of some kind is taking place, and what we want to do is calculate probabilities. Now, here we're going to do something simple. We're going to roll a pair of dice, but we're not going to look at the individual numbers, we're just going to note whether they're even or odd. And the advantage of doing that is that it reduces the number of outcomes quite considerably, because when you roll the dice, there's technically 36 different things that can happen. If you only pay attention to evens and odds, then there's only 4 things that can happen. What are they? You get even followed by odd, or we start with even followed by even followed by odd followed by even, and odd followed by odd. Now, by the way, if you're interested, they're actually, with a pair of dice where there are 36 possible outcomes, there's 9 different ways of getting 2 consecutive evens. There's also 9 ways of getting evens followed by odd, 9 ways of getting odd followed by even, and 9 ways of getting 2 consecutive odds. So therefore, each one of those outcomes has the same probability, which is 9 out of 36, or 1/4. And by the way, if you're not sure, you can sit down and make up a list of all the different outcomes that can occur with a pair of dice and confirm that these are true. It might take a while, but you can certainly do it. And by the way, here's a hint. If you did it in Excel, that would speed it up a lot. Okay. All right. Anyway, so right off the bat, we have an experiment taking place here where we know that there's only 4 possible outcomes, and each one of these has the same probability, which is 1/4. All right. So that's a nice, simple setup. And what we're going to do is, by the way, we're going to use the following notation. Even followed by even, from now on, we'll write it as EE. And of course, you can see the others as well, because it saves us writing. So we'll write them as EE, EO, OE, and OO. Great. Now, we're going to introduce our first key concept here, the notion of a sample space, which is simply a set that contains all the different possible outcomes of our random experiment. This shows me all the things that can happen. Just like with the roulette wheel, the sample space would be the numbers from 1 through 36 and 0 and 00. All the probabilities of interest to us are calculated based on the sample space. It's the starting point for all of our calculations. it shows us the range of possibilities. Okay. Now, now we're also going to introduce the concept of the event. So within a given sample space, there are many different subsets that can be created. So here's a good example. What if I am interested in knowing that in a game like this, what is the probability that I get at most one even number, which is basically means I get either one even number or no evens. Suppose that there's some prize involved. I'll win a prize if this happens. And I want to know the likelihood of this happening. Well, as you can see, the set F contains the outcomes OO, OE, and EO. In fact, the only thing that's missing is the EE because that would be two evens. Okay, now the key detail here is that F is completely contained within S. And that means that F is a subset of S. And in probability theory, we call that subset an event. Okay, now you've seen the word event many times. Here it specifically means a subset of the sample space. Okay, because all these elements are in the sample space. You can see it up here. F is part of S, and therefore F qualifies as an event. Why does this matter? Because we typically will want to calculate probabilities of events. How do we do that, though? All right, well, there's actually a couple of ways of doing this, which we'll see. And in our example, remember, each of these outcomes is equally likely, and that does speed things up. But we need to have an approach that will work even when they're not equally likely. So we're going to see both. How to do this when they're all equally likely and when they're not. But before we do that, I see that it's 11:15. So since we're having a full session today, I think we need a break right about here. So we'll stop and do something else for 15 minutes, probably eat or drink something. And then when we get back at 11:30, we'll dive more deeply into this probability theory. And you'll see it's a very interesting area. It's really very, very important in statistics, but it also has applications in many other areas as well. So, and we'll run into these concepts again and again throughout the course. All right, so let's knock it off here. And when we get back, hopefully this PC will still be running, and then we'll take it from there. All right, oh, I forgot. I usually try to pause the sharing here because otherwise on the recording, I think this prevents me from having a bunch of blank space. So let's see how that works. All right, see you all in a while. All right, here we are. Oh, I better get this back on. All right, so again, the whole idea here is that we're looking at a sample space which contains all the different possible outcomes of a random experiment. And then on that sample space, we can define any event that we want. And we're going to use the techniques in this chapter to calculate probabilities. So in this case, as we've already seen, each of these outcomes is equally likely. So calculating the probability of F is a very simple matter. But before we do this, I just want to remind you that each of these has the same probability. And since there's 4 outcomes, by definition, each one must have a probability of 1/4. So F, being composed of EO, OE, and OO, what we can do is calculate its probability by taking the probability of each individual element and then simply adding them up. And so that means that the probability of this happening, getting at most one even number, is 3/4, or 0.75, of course. All right. Now, in a case like this, though, when the, let me just leave it there for a second. When the outcomes are equally likely, though, we can actually speed things up just a little bit because we know that there are 3 outcomes in F and 4 in S. And again, because they're all equally likely to occur, what we can actually do, instead of calculating each individual probability and adding them up, is what we can do instead is take this ratio where we take the number of events in any given event, a number of given elements in event E, and divide it by the number of elements in the sample space. But only if each different possible outcome is equally likely. So in the case of F, the probability of F would be the number of elements in F over the number of elements in S, which is also 3/4, as we saw earlier. So this is a shortcut that is available to us when each element or outcome in our sample space is equally likely. But just keep in mind, this approach always works, okay, no matter what's going on. This approach only works when each element, or I should say, I guess we could say each outcome is equally likely. All right, so you can decide in each case which one you want to use as long as these are equally likely. But when they're not, we have to use this approach, calculating each one separately and adding them up. All right, so this is very straightforward. Now, as we'll see, of course, it'll get more complicated as we move along and we start looking at more complicated examples. But as a starting point, it's pretty straightforward to see what we're doing. We have the random experiment. We have different possible outcomes. We define events, and then we can use this information to calculate probabilities. Let's see. Yeah, here it is. So this is the case of F. We have 3 outcomes in F, which are equally likely. We have 4 in S, which are all equally likely. So that probability is simply the ratio of 3 to 4, or 0.75. All right, now with those definitions out of the way, we can move on to something a little bit more important, which is a series of propositions on which all of probability theory is based. And because they're so important, they're referred to as the axioms of probability. Now, the last time you saw the word axiom was probably in high school geometry, where you saw them all the time. An axiom is simply a statement which is accepted without proof. Axioms form the foundation of any system of logic, and so it is unique to each different discipline. And in the case of probability theory, all of our results are based on the following three axioms, which we will assume are true, and develop more results from there. Okay. Now, it turns out of the three, the first two are very straightforward. The third one is a little bit more challenging. All right, let's see what they are. Now, number one, we're going to state right up front that it's not possible to have a negative probability. Instead, we're going to claim that all probabilities have to be somewhere between 0 and 1. 0 means that an event is impossible, and 1 means that an event is certain. It's guaranteed to happen. And then all other probabilities are going to fall somewhere in between. So axiom 1 simply tells us that each individual event has a probability which may not be negative. Then we're going to also claim that the probability of the entire sample space is 1, because no matter what happens, something in that sample space has to be true. All right, so when you're rolling the dice, for example, one of those 4 outcomes has to occur with certainty. So the probability of the entire sample space is defined to be 1. And when you combine these two, that means that every single probability is going to be somewhere between 0 and 1. So in other words, a negative probability would be meaningless, as would a probability of greater than 1. Now, it doesn't have to work this way, but this is what makes sense. And so this is why mathematicians chose to develop probability theory based on these 2 axioms, plus the one that's coming up next, because the whole thing is easier to understand when we define all probabilities to be between 0 and 1. Now, the third one is a little trickier, and we'll see how that goes, but it'll make more sense as we go along and learn more about probability theory. For now, let's just take it for granted that this third axiom is something we'll assume. And what is it actually telling us? Well, before I show it to you, I just want to quickly review a concept with you from set theory. And so just imagine we have 2 sets. Let's not call them S. Let's call them sets A and B. Suppose A contains the elements 1, 2, and 3, and B contains the elements 3, 4, and 5. We can define the operator union to represent the combination of all the elements in 2 different sets. Okay, so in other words, A union B is the set of all elements in A or B or both. And so in our case, you would end up with 1, 2, 3, 4, and 5. Basically, I've just created one new gigantic set from A and B. And if you notice, 3 exists in both sets, and so it is in the union, but we do not list it twice. With sets, we only want to list the unique elements. There's no need to repeat the 3 twice, because it's understood that the set simply represents the different or unique elements in this union. So the union simply means combine 2 sets. That's all it is. And by the way, in terms of just English, union is equivalent to the word or. And in fact, some textbooks write this as A or B for that reason. So it's possible that if you've encountered this in the past, you were not introduced to this symbol for union, but instead you were using the word or. They mean the same thing. Now, I also want to introduce you to another important concept with sets, because again, we'll need this to understand the third axiom, the scary one. And that's this. Suppose I have two sets. A is this time 1, 2, 3. And now let's introduce C, which is 4 and 5. So A union C, as you can imagine, is 1, 2, 3, 4, and 5. But A and C have no elements in common. And they're said to be mutually exclusive. So just keep that in mind. Mutually exclusive means they have no elements in common. Now that's going to be important when we introduce the next set operator. And so let's take a look at that. First of all, let me rewrite here what we've been defining here as A, B. Oops. B is 3, 4, 5. And then C was 4 and 5. So we're going to introduce another operator. This is called intersection. And this represents a set containing all elements in both A and B. Okay. It has to be both. This time it has to be both. So let's show what we get if we write the intersection of A and B. The only element they have in common is the 3. What about B and C? They have the elements 4 and 5 in common. But what about A and B? A and C? They have no elements in common. Okay, so they have no elements in common. And their intersection is the empty set, we call that. And we also then can say that because of all of that, A and C are mutually exclusive, meaning they have nothing in common. One more thing, in terms of English, this is often represented or replaced by the English word and. I did it again. Just want to throw that out there because some books use the word and instead of the intersection symbol. So intersection means we're taking two sets and finding what they have in common, if anything. If they have nothing in common, then their intersection is the empty set, which means that these two events are mutually exclusive. Now, if you want to think of some real world examples of mutually exclusive sets, it's not hard. For example, the even and the odd numbers are mutually exclusive. Or the red cards in a deck and the black cards in a deck, they're mutually exclusive. How about the white and the black pieces on a chessboard? Mutually exclusive, okay? So there's a lot of examples out there. Most of the time, I mean, well, I shouldn't say most of the time, but in many cases, there are at least a few elements in common between sets, but not always. Now, with all that being said, the third axiom hopefully will make a little bit more sense. And okay, now I lost it. Here it is. If we have a group of sets or events that are mutually exclusive, the probability of their union is equal to the sum of the individual probabilities. Okay. Now you can see the way it's written, it's a very general expression because it's basically saying this can apply to any number of sets. No matter how many there are, as long as they do not overlap with each other, the probability of this union equals the sum of the individual probabilities. Wow, that's a big one. But we'll get to see more of this as we go along, and it'll make more sense. And just as a quick example, if I had something like this, a very simple case, it means this. As long as A1 and A2 are mutually exclusive. But the point of this is that you can do this with 3 or 4 or 5. It doesn't matter as long as they're all mutually exclusive. Okay, now, with that being said, what we're going to do is start calculating more advanced probabilities. All right, leaning on these axioms, we can now create more complicated situations whose probabilities we can calculate. For example, now, oh, by the way, and this leads us up to the introduction of what we're going to call the rules of probability. And these rules are meant to apply to more complex cases. All right, we've got the addition rule, the complement rule, and the multiplication rule. Now, the first two are pretty straightforward. They're not that complicated. The third one is a bit tricky. So we'll start with the first two, and we'll work our way through them, and you'll see that they're not that bad. The third one requires us to do a little bit of a detour to understand it a little bit. We have to introduce some more new concepts before we tackle the multiplication rule because it is kind of complicated. Now, the purpose of these rules is to tell us what to do if we want to calculate the probabilities of combinations of events. All right. In other words, 2 or more things happening at once. We want to understand how that works with these rules. So where should we start? The addition rule. Now, the addition rule is designed to help us understand what happens when we have a union of 2 events. Okay. And of course, this symbol means union. If you forget it, of course, it looks like a U. And what it's telling us is that we have the probability of A plus the probability of B, but then we subtract the intersection between them. Now, just to illustrate why this is necessary, you're probably wondering, why do we have to subtract this intersection? Well, I'm going to show you a diagram, which you probably have seen before, which will help us understand why this is necessary. Why can't we just add up the probabilities of A and B? All right, so this is, again, a diagram you might have seen before, but maybe it's been a while. Let's see what this thing looks like. It's basically a big box. And then we have circles. Let's say this is A and this is B. The box represents the entire sample space. And this diagram is called a Venn diagram. Hopefully, I mean, that might trigger some memories. You may have seen this before. And so what it does is it shows the relationships between different sets. So let's imagine now that A contains 1, 2, and 3, and B contains 4, 5, and 6. The entire sample space is 1 through 6. Oh, I'm sorry. Wait, sorry. I just realized I messed it up. This is supposed to be 3, 4, and 5. And then the entire sample space can be 1 through 5. All right, so we have 1, we have 2, we have 3, we have 4, and we have 5. So this is A, and this is B. And where we have this cross-hashing, that's the intersection between them. So here's the challenge. We want to calculate the probability of A union B. Oh, and by the way, we're going to assume that each of these is equally likely. So therefore, the probability of A is 3 out of 5 because there are 3 elements in A out of a total of 5 in the sample space. Then with B, based on the same reasoning, it's 3/5. The intersection between the two, because there's only one element in there, is 1 out of 5, because A intersect B is just the element 3. Now, if you take, and you want to calculate this probability, and you try to just add up these first two, you're going to get 3/5 plus 3/5, which is 6/5, which is obviously impossible based on the axioms of probability. Why did this happen? Because each of these includes the number 3. It's being counted twice when we simply add these together. Okay, so how do we work around that problem? Oh, we have to subtract the intersection, don't we? So I guess I have no space for that here. Let me move that to the next slide. So this which is impossible according to the axioms. The 3, I should say the set 3, or no, the element 3 is fine. The 3 is being counted twice. Because it appears, or it is an element of both sets. How do you correct for that? Well, this can be corrected for by subtracting. The element 3 as follows. The probability of A union B is the probability of A plus B, but then we're going to subtract that intersection because it is being counted twice. And look what happens. All of a sudden, you've got 5/5, which is 1, which is correct because, as you can see, A union B gives us back the entire sample space. So what you've essentially done here is you offset the double counting of that intersection when you subtract the intersection at the end. It's done to avoid double counting whatever's in that intersection. So that's why we have to subtract in the addition rule. And so you can see it clearly does a good job giving us the final result, as long as we make sure to subtract whatever is in common to the two sets. All right, so that's our addition rule. Now, see, that wasn't hard. So let's look at some examples of this. Let me leave this there for a minute for you to catch up. And then we're going to do some examples with our dice rolling experiment where we had all evens and odds, and we'll see how this works. All right, so let's go back to the dice rolling experiment. Remember, the sample space was simply EE, EO, OE, and OO. We can now define any events we want on that sample space and come up with probabilities. All right, so here we go. Now there's your sample space. Let's say that we define the event A to be the first roll is even, and B is the event that exactly one roll is odd. So you can see I've written out all the elements in both of those sets. And what we would like to know is the probability of A union B. Or in other words, another way to say it is that we want to know the probability that the first roll is even or exactly one roll is odd. Let's say that you're playing a game in the casino and getting a prize depends on one of these two things being true. It doesn't have to be both, but one of them will give you a payoff. How do we figure out the probability of that happening? Well, we're going to use our addition rule. Now, by the way, if you notice, there is an element in common between these two. A intersect B equals EO. So they're not mutually exclusive, and we do need to subtract this for our calculations. All right, let's see how this works. All right, so yes, we're trying to find out the probability that either the first roll is even or exactly one roll is odd. So we'll look at the individual components of the addition rule. And we'll calculate each individual probability using this approach, because remember, every one of these elements is equally likely to occur. So we can take advantage of that. And we can see that A must therefore have a probability of 2/4 or 1/2. B must have a probability of 2/4 or 1/2. And A intersect B must have a probability of 1/4, because that is coming from the number of elements in each of these sets compared to the overall sample space. All right. Now, let's use the rule. And we combine them together and we discover that it is in fact 3/4. All right, we add the 2 1/2s and we subtract the intersection and we end up with 3/4. Now, if we want to, we can create a Venn diagram for this. EE, EO, and OE. If you notice, OO doesn't belong to either one of them. So you can see that the union consists of the elements EE, EO, and OE. And guess what? The number of elements in this union divided by the sample space is 3 out of 4. So for this reason alone, or for this additional reason, the probability of A union B is also 3/4. In other words, there's 2 equivalent ways of getting to this result. We can use the addition rule, or we can use this approach because all the elements in our sample space are equally likely. And you can use them to confirm each other too. Okay, you're not required to do both approaches, but you do see that they have to give us the same results. Excellent. So that, by the way, when we have more than one probability involved, we often call these compound events, meaning that there's at least 2 things going on. And so the rules are telling us what to do when we have these different compound events. The individual events, we know what to do, but now we can handle these compound events as well. Now, by the way, because, oh yeah, here I did the same thing here. Just because you might be interested in this, let me just show you what would happen if we had 3 events. Okay. It gets a little bit messier with 3 events. I don't want to waste too much time with this, but I want to show you that you can take this rule and extend it to 3 events, but it's a little bit messier. I'll show you why. All right, let me show you a Venn diagram. Oh, this is going to be a mess. Actually, I'm going to make these circles a little bigger so it's really easy to follow. Oh, well, it's not much of an improvement, but so here's A, B, and C. So you can see there's a lot of overlapping here all of a sudden. Let's see. This will be A and B. This will be B and C. And then that will be A and C. So it turns out that when you have 3 of them, there's actually a piece in the middle that overlaps between all 3 of them, which has to be taken into account. So let me show you how messy this gets. We're not going to actually do this on any of the tests, by the way. This is just for your own benefit. When we have 3 of these, watch how messy it gets. First, we subtract all the intersections. But unfortunately, this causes us to over subtract the area that is common between all 3 of them. And so we have to add something back to get our final results. So yeah, ooh, that's getting a little messy. Oh, you know what I just realized? Let me just do something here. I just want to be consistent. There we go. That's better. All right. So in other words, we have the individual probabilities added up. We subtract the intersections between each pair of events, A and B, A and C, B and C. But then because that over subtracts, we need to add back the intersection between all three of them. Wow, you can imagine what this is going to look like with 4 or 5 elements, sets rather. It's going to get really messy, but because every time we take away, we might be taking too much away, or we might be not taking away enough. So we have to compensate for it somehow. So don't worry, we will be sticking with only cases where we're combining 2 events, not 3. But I just want you to be aware that you can do this with 3 or more, but it gets much more complicated. All right. Okay, now let's go on to a special case though. What if we have a situation where we want to combine A and B, but it turns out that they're mutually exclusive? That's interesting. Now what do we do? Well, why does this matter? Because remember, the probability if A and B are mutually exclusive, then their probability of their intersection is 0, because the probability of the empty set is 0. So you know what that means? In this one special case, because this last probability is 0, there's no need to subtract it. It's not necessary. And so therefore, we can create what's known as the simplified rule, or the simplified addition rule. And it looks, let's see, where is it? I'll just write it in here again. Uh-oh, I think I hit the wrong button. Here we go. I'll just write it back in here. The simplified addition rule means that all we need to do is combine these 2 probabilities. Okay, so the simplified addition rule is used just for these cases when the 2 sets have nothing in common. Now, if you forget and you use the full rule, it won't matter because you'll still end up subtracting 0. But I just want you to be aware that there does exist such a rule. There we go. All right, so we've got the full version of the rule and we have the simplified version, which is only used when A and B are mutually exclusive. All right, it doesn't save us that much time, but it's good to know. Let's see if I have an example here. Here we go, back to the original die rolling experiment. Now this time, let's say that A is the event that the first roll is even, and B is the event that this first roll is odd. Now, clearly, those are mutually exclusive events. The first roll can't be both even and odd. The intersection is the empty set. And that in turn implies that this probability is just 0. Well, what do we want? If we want to know the probability of getting A or B, because let's say there, again, there's a prize involved in the casino. What we can do, by the way, you can always go ahead and start calculating these probabilities because we'll need them in the formula. And you can see that this one is actually 2/4 or a half, and so is this one. Their intersection, the probability of that intersection is 0 because it's empty, right? A and B is the empty set. Very good. So let's do it. Throw these in, and what do you know? It just adds up to 1. And remember, we define 1 to be a certain event. And you can see why, because we're being asked, what is the probability that the first roll is even or odd? Well, one of those two things has to be true. Therefore, we call this a certain event. It therefore must have a probability of 1. All right. Now we're ready for the next of the compound rules, the so-called complement rule. Now, before we go into this rule, we have to explain what the word complement means in this context. Now, you hear the word complement used in different ways, and there's also an equivalent word. Remember, there's another word spelled in a very similar way. Compliment with an I, that's not the same thing. This compliment means you're saying to people, hey, you look nice today, or something like that. Compliment with an E means these are two things that go together somehow. In fact, you might remember if you've ever taken an economics class, complementary goods are consumed together, like peanut butter and jelly, for example, or hamburgers and ketchup, hot dogs and mustard, that type of thing. They go together. So here, though, what we're trying to do is find events that have two very important properties, which are listed right there. Number one, their union is the entire sample space. And number two, their intersection is empty, which means A and B are mutually exclusive. If both of these things are true, then A and B are considered to be complements. Now, let's think of an example of this. All right, first, let me give you a chance to catch up. We're going to think of an example, and then when you see even one example, I think this will start to make a lot of sense. And in fact, you should be able to come up with a lot of your own examples. What if we're thinking about a deck of cards? Our experiment consists of choosing a single card from the deck. And our only interest is in what color is the card. Now, if you're not familiar with cards, by the way, there's 52 cards in the deck, half of which are red and half are black. That's all you need to know. All right. Now, you may already know more, like you know what the suits are: spades, hearts, diamonds, and clubs. The spades and the clubs are black. The diamonds and the hearts are red. Within each suit, we have 13 cards ranging from ace up to king. But for here, we only need to know that there's 26 red cards in the deck and 26 black cards. Now, the question is whether these properties are satisfied for the red and the black cards. Well, let's say A represents the event that the card is red, B is the event that the card is black. Is there a union? The samples, by the way, the entire deck is the sample space in this case. If I combine all the red cards with the black cards, will I get the entire deck? The answer is yes. On the other hand, is it true that no card is both red and black? Yes. So no card can be both red and black. That's what this statement means. This top statement could be interpreted to mean that all cards are either red or black. Okay, in other words, there's no green cards in there, for example, like with a roulette wheel, there are those two red-green numbers. Not so here. all the cards must be one or the other. And so therefore, since both of these conditions are true, A and B are complements. All right, complements. Now, let's think of another example. And there's so many of them. It's not that hard to come up with. Let's say, how about the white and black pieces on a chessboard? Well, all the pieces must be either white or black, but none of them can be both. So there you go. What else could we come up with? All right, how about this one? Among the positive integers, the odd numbers and even numbers are complements. Why do I say that? Because once you start with 1, all the positive integers have to be either odd or even, but it's not possible to be both. So those would be considered complements within, the positive integers, because odd and even only applies to the integers, the positive integers. In other words, -7 is neither even nor odd. It's not, we don't think of it that way. And certainly the fractions cannot be either even or odd. But anyway, these are complements. Now, with all that being established, if we know for a fact that an event A is a complement, if A and B are complements, then, here's another one I dreamed up. American League and National League teams. If you follow baseball, you know that all of Major League Baseball consists of both the American League and the National League. There's no teams that overlap between them. Anyway, we can then apply our complement rule. Now, first things first, we're going to use the little c to represent complement, okay? So whenever you see that little c there, it means that's the complement of that event. And based on the definition of complements, this means that A union A complement is the entire sample space. And in addition, A intersect A complement is the empty set. This is what it means to be complements. All right, well, guess what? This gives us a very easy set of rules. There's 2 equivalent versions of this rule, by the way. Let me show them to you. And by the way, the implications of all of these definitions are that the probability of any event and its own complement have to add up to 1, because one of these must be true. Algebraically, we can rewrite these in 2 different ways, and these both are what we mean by the complement rule. Okay. Oh my God. This is getting very intense, isn't it? Let's look at a quick example now. Now, same thing with the dice. The original experiment. And so this time, we define A as the second roll is even and B is the second roll is odd. Are these complements? Good question. How do you know? There's 2 things that have to be true. Is their union the entire sample space? And are they mutually exclusive? Let's find out. Well, all right, actually, let's do this in a separate slide. Are A and B complements is equivalent to asking, Are A and B mutually exclusive? And are A and B, or I should say, do the union of A and B, does the union, what am I doing? Does the union of A and B equal the entire sample space? Well, let's find out. Let's write them down again. A is OE and EE. And B is EO and OO. Okay, so this question, what do you know? They have nothing in common. So the first question is correct. Is there a union in the entire sample space? Well, let's write out all the elements. And yes, indeed, these are, both the conditions are met. So the conclusion to this is that A and B are complements because both conditions are satisfied. Beautiful. Well, if that's the case, then we can calculate any complement we want. So let's say that we're interested in knowing the probability of a complement, which, by the way, in this case, you could make the following claims. B is the complement of A, and A is the complement of B. They're both true. Okay, so let's say that we're interested in knowing the probability of A complement. So the probability, since B is the complement of A, we're going to wind up with probability B, because they are in fact complements of each other. Okay, and that's all we have to do. It's very simple. So just apply this rule, and there you go. Wow, that was easy. As long as they're complements, this rule can be applied, and it's a breeze, isn't it? Sadly, though, the next and final of our rules, and I've summarized them right here, by the way, the multiplication rule is a little bit messier because we have to introduce 3 new ideas before we even look at it. Now, it's not going to be as painful as it sounds because I can show you all of this with one simple example, but we definitely don't want to start it now. Not 12/28 or whatever it is before Christmas. No, that just doesn't work. So we'll stop here, and I'll post all of these notes, of course, and then next Monday we'll get together at our normal time and carry on with 5, and then by Tuesday you should have the chapter 3 problem set done. In the meantime, go ahead and have a great Christmas, and you don't have to feel like you have to think about this stuff at all, but maybe on Sunday night start flipping through your notes again and getting ready for Monday's class. Okay, so in the meantime, I hope you all have a great holiday. Oh, wait, I missed a chat here. Hold on. Oh, you're welcome, everyone. Yes. Okay, so yes, I don't know about you. I'm looking forward to Christmas. It's been a long year, that's for sure. And I think we deserve to have a nice Christmas. So I'll see you all on Monday. Okay. All right. Goodbye. You're welcome, everyone. Happy holidays.